Hello everyone. So let us continue. So this is question number 12 of GATE 2023 mathematics paper. The question is you are having four sets X, Y, Z and W, and the question is whether which one of them is homeomorphic to what. So let us quickly know what is the definition of homeomorphic. See, in topology, you can consider two sets as a homeomorphic, or you can say a rubber sheet geometry. A rubber sheet geometry, that means what? Suppose you are having a square, then you can just stretch it. You can make it like this, correct? And you can cover it with a ball. That means this can be made as a circular part and something like that. Everything whatever you can do with the rubber, you are having rubber ball and whatever things you can do with this, so that without breaking it, whatever thing you can make it as a square, or as a cube or something like that, without making the breaking the parts. That's what you should understand what is homeomorphic, when the two sets are homeomorphic. Okay, that is basic definition. And if you try to see the mathematical definition, then you should be able to find a function from the set x to y. See, if I am saying x is homeomorphic to y, homeomorphic to y, that means I should find a function from x to y which is bijective, and it should be continuous, and the inverse f inverse, it should also be continuous. Your function is continuous, f inverse should be, see this, since the function is bijective, it is invertible, it has inverse, and this inverse should also be continuous. If these three conditions are satisfied, then you can say that these two sets are homeomorphic to each other. Okay, now what are the benefits if the sets are homeomorphic? If the two sets are homeomorphic, there are some properties, that is homeomorphic invariant, that they satisfy. That means if x is complete, then y is also complete, and vice versa. If y is complete, then x should also be complete. That means completeness is homeomorphic property, homeomorphic invariant. And then same goes for compactness. If one is compact, then other should also be compact. Next, if one is connected, then other should also be connected. If one is path connected, then other should also be path connected. So these are the homeomorphic invariant. Um, what is the benefit of this? The benefit is that suppose you are having two set, say one is connected and another is not connected. So there cannot be a homeomorphic map from x to y, correct? There cannot be, you cannot have a homeomorphic image from x to y. They won't be homeomorphic. Suppose one set, the set x is compact, another is not compact, then they are, you cannot say that they are homeomorphic, so they are not homeomorphic. Is that okay? So now let us try to see this question. Okay, so I'll just erase this. Let us see one by one what are the all the sets are. Look at the first one. What is the set x? uh, Everybody is in R3, yeah. All the four sets are in R3. So let us try to draw. They will be having a 3D image. So I'll just try to make sure that whether you should understand it. Let us first consider the 2D image. Suppose I'm having mod x plus mod y, and say it belongs to rational. It belongs to rational means what? It can have any number. Say I'm saying 1. So what is the graph of mod x plus mod y equal to 1? So if your x is positive, then this will be x plus y can be positive and negative. So x plus y equal to 1. This will be a straight line. X minus y equal to 1. Then minus x plus y equal to 1. And minus x minus y equal to 1. These are the four straight line. So the graph of this guy, mod x plus mod y, will be the something like this. So this part, this is your graph. of mod x plus mod y equal to 1. That means this is a square. Okay, this is the graph of mod x plus mod y equal to 1. What I have done, I have just drawn x plus y equal to 1, which is this equation, x plus y equal to 1, and then others also. I have drawn all the four corner lines, and then I am able to find it is like a mat like structure, that is a rectangle structure. This is what, so I will try to extend this notion here in 3D. Suppose I'm having three variable mod x plus mod y plus mod z belongs to q, then what happens actually? So I'm having mod x plus mod y plus mod z equal to 1. So I'll be, how many equations I'll be having? And if you try to expand this guy, then it will be a cuboid. I'll just give you a simple example of a cuboid. It will be something like this. Sorry. It will be something like this, something like a cubical shape I'll be having. Earlier in two dimension I was getting a square, and here I will be getting a cubical shape. So now I have understood what is the shape of this guy. This is a cube, or maybe cuboid if the length are not same. So for this I know, and let us see the second, y equal to xyz equal to 1. As I told you, we are going to see rubber sheet geometry. See, R3 is non-linear space, so there is no problem by homeomorphic invariants. So again, xyz equal to 1, this is the function I am having. I know the graph of xy equal to 1. What is the graph of xy equal to 1? The graph is something like this. How do you draw the graph of xy equal to 1? Would you observe x equal to 1 upon y? That means if your y is very high, then x goes to 0. If the value of y is very high, correct, then that means if y goes to infinity, then your x goes to 0. Do you observe? If I increase the value of y, then the value of x is going towards 0. It is coming to the y-axis, something like that. So this is the graph. Okay, now if you try to make it x y z equal to 1, what it will be? It will be like something similar to that, but it will be something like a mat here. I'll just make sure. It is something like a mat which is covering that side, and there will be a mat which is covering this side. There will be a mat which is covering this side, and so on. Okay, all the possible combinations will be there. Okay, so in all the quadrant octant actually I'll be having this type of figure. I'm having something like a mat. Earlier I was having only the curve, now I'll be having collection of curve, correct? So it will be looking like a mat. It will be something like this, which is that side, and I'll be having one more mat which is that side. So they are actually disconnected. So now I know what is the graph of the second guy also. Okay, now look at the third one. That is very simple. That is a sphere, and so I don't have to struggle for that guy. What is the graph of this? You know, it is something like mat-like structure here, 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 something like this. Okay, now look at the z. This is x square plus y square. I know this is a sphere. This is a sphere centered at 0, 0, 0, and radius is 1. And what is this last guy, xyz equal to 0? This is possible only if either x is 0 or y is 0 or z is 0. That means it will be taking all the coordinate axes. This is the only line. It will be taking this line, it will be taking this line, and it will be taking this line. So only lines will be there. Okay, now I know the graph of this guy also. It will be containing all the lines. Now let us try to see the options. Okay, okay, the first question is whether x is homeomorphic to y or not. Look at this, your x, it is actually a compact set. If you don't want to say compact, it is connected. Actually it is connected. And look at the second graph, y, it is not connected. One at the one place I am having this guy, this is a cubical shape, and other I'm having something similar to here, it is having this structure. So if I'm having 2 point, 1 point here, 1 point, I cannot find a connection, I cannot find a path to reach there. So this is not path connected. Whereas if I take any 2 point here, I can always find a path. I can always find a path. I'll be going here, I'll be going here like that. Then because everybody is here in this case, whereas if you take a 1 point here, you can I won't able to get in. So if there is a homeomorphism from x to y, then that should this function f, correct? If there is a if this function is homeomorphism of x and y, then if x is connected, then y must also be connected. If x is path connected, then y must also be path connected. Now I have seen that this guy, this cubical shape, this is path connected, but what about y? It is not path connected. So option 1 is wrong. This is not true. Now let us next question, next option. Z is homeomorphic to w. What is z? Z is your sphere, correct? And what is your w? W is just this guy, axis. Is it homeomorphic? If you see, this guy is compact, and whereas this guy, it is actually not bounded, so it won't be compact, isn't it? Because if it is bounded, then only if it is compact, then it will be bounded, but it is not bounded. So because this length can be infinite, there is no bound that it will be having only this guy or something like that. There is nothing. So this guy is compact, this is not compact. So there cannot be a homeomorphism between these two. As I told you that this is the homeomorphic invariant. So this is again wrong. What is the next one? Yeah, y is homeomorphic to w. Look at your y and look at your w. What do you observe? Again, one more thing. Do you observe? Look at the graph of y. The graph is something like this. Something like, again, it is not path connected. And what about w? And what is the graph of w? It is just axis. Everybody is path connected. If I want to go from here to here, I can go. I can walk from here and here. I can go from here to here and so on. Correct? So if I'm having 1 point here or 1 point, I cannot go from here to here. So this is also wrong. So this option should be correct. So what are they? What is this? X is not homeomorphic to W. Look at your X and look at your W. Again, what do you observe? Your X is your cubical shape, correct? And what is your W? This is a cubical shape, and your W is the axis. Okay. These two is again also, it is not homeomorphic. Why it is not homeomorphic? You can see there are so many conditions. This guy seems compact and this is not compact, or other homeomorphic property also we can check about completeness. Yeah, this is complete, because compactness I think we cannot see, because it belongs to Q. Q can take any numbers. Okay. Mm, compactness, completeness, path connected. It is both are path connected, and yeah. So in this case, actually, see, for this question, we are able to solve this question because others option A, B, C were not true. Uh, X is not homeomorphic to W, so option D must be correct. Suppose this is homeomorphism. Suppose there is a homomorphism from X to W, correct? And what can we say about the set X? It is having all the cubical shape, so it will be covering whole of plane. It will be covering all R3 if you see only the rationals one, because between any two rational there is a rational, so it will be having one cube, another cube, and so on. There will be so many cubes I'll be having some gap between them. Do you observe the gap? Because there is some irrational numbers also in between. Okay, so again they are not path connected if you take different queues. If I am taking only one queue, that is okay, but if I am taking, yeah, this is the good example to visualize, because here mod x plus mod y plus mod z belongs to q. That is what they are saying. Okay, so it is not just one cube, it has so many cubes. We will be having some more cube containing that, the smaller one, and they are disjoint because this guy belongs to rational, so there are between two cubes there is some irrational number also, correct? So everybody is disjoint here. Every cube is disjoint here, so they are even not connected. If you take one point at this guy and one point at this guy, they are not connected. Okay. Yes. Okay, now then there is a question that we can encounter. Look at the first option which I discarded, that is X is homeomorphic to Y. Now actually in the beginning I told that one is connected, other is not connected, so that won't be the reason here. Do you see why? Because if you see that, what is the first guy? What is the set X? It is all the cubes. Okay, something like this. One cube is inside, one cube is inside, something like this. Okay, so, and whereas in other case, every cube is inside, one is, but it is completely disconnected, huh? And it is going up to infinity, so there are infinite connected component. Oh sorry, countably infinite, because rationals are countable, so there are countably infinite connected component. What do you mean by this? That means the first cube, this is one my connected component because everything is connected here, and second cube, it is again one more connected component of my set. So I'm having this first component, second component, third component, and it will go with all the rationals. Whereas in the case of Y, if you see, it has only how many octants, it will have that much only, these three type of, correct? So it is finite. Here it is connected. So homeomorphic invariant, if there is a function from X to Y which is homeomorphic, then the number of connected components also should be same. that is number of connected component in X should be same as number of connected component in Y. Whereas if you see in the set X, there are countably infinite connected component, and whereas in the other set there is only finite connected component. Okay, so still the option A is wrong, option B is wrong, and option C is wrong, and option D is also D is correct, because it is saying X is not homeomorphic to W. Okay, thank you so much.